So you may, um, you know that we're working on a rock climbing robot. So I'm not sure if you've seen those videos, but I made the handholds now so that the simulation of the robot can actually hang in the wall there and climb. And then while I was trying that out, I also got my robot to do a little somersault off the wall, which I thought looks kind of cool. So this is running using the Mujoko simulator. And then based on that, we can implement the planning. Let's go to we'll record this as well. Maybe. Yep. It used to be a simpler URL as far as I remember. Oh yeah, there you go. Then hopefully can connect here. and that doesn't work anymore. So we could use any other video. So let's think about what kind of video we want. In the meantime, I can download this. This is weird. It used to use different. I thought you can upload it. Yeah. So today I want to talk about optical flow. So that only works if the pictures are moving. Um, but now I cannot download from YouTube anymore, and so I'll have to upload the file, which is okay. And then share it. slides, and now let's see what we can do with that. Okay. Oh no, this wouldn't work. Good. Okay, so here we have a small test video of what I want to show. So this is just me walking through the corridor in the third floor here. You may have seen it. Now, how did I move? Like if you draw the map of what movements I made, then what did I do? Any ideas?
Small zigzag forward and then zigzag back.
Yep, exactly. And how do you know? Huh?
I'm human.
Human, I'm smart. Actually, that is very smart. It's one of those things that humans can do, and we know how to interpret the world around us. But to implement that on a computer is actually non-trivial. Let me just see, because I just want to make sure I don't miss any messages about things. Okay, this one is not one. Ah, okay, let's go back. um, we know how if we have a model of the environment, then we know how, when we move through that environment, how the images should change, right? And that's something that we're very good at. So we don't really make mistakes often when we're doing that kind of processing or reasoning. Now, for the computer, that would be a really good ability to have, right? At the moment, because what that allows us to do is, if I can look at the part of the environment, then I can understand what I'm seeing. Then I move a little bit. Now I can sort of estimate how I move, right? Using the visual feedback. Then that's quite useful, because now I moved there, so now I know that position is related. I moved forward by 20 centimeters. Now I turn a little bit. Now I see a new part of the environment, right? Which I think then can stitch together in order to make a map of the entire room. So that's basically the crux of robot navigation. If we can do that, then we can put the robot down in any environment, and we can then have it drive around a little bit, map the environment. Afterwards, it knows how to plan any kind of path through that environment. Can figure out, oh, if I want to leave through that door, I can drive this way, and then I can go out. So this is a really cool ability to have. It's kind of fundamental. If you can't do that, then what could you do? Yeah, somebody could tell you the map, yeah, but their humans aren't really that good, right? And it's interesting, because let's think about that, and you're trying to explain to me how to go to. You're in the Mandarin Training Center, right? So I've never been there. That's why my Chinese is so bad. So how do I get to your professor's office? You do go to class, right? You know who your professor is.
Leave this room, go downstairs.
Okay.
Go up the building, go across.
Yeah. Okay, I don't actually know where the MTC is. So you cannot just say go to the MTC. Otherwise, every navigation problem could be trivially solved by saying go to your goal. But it's interesting that the hints that you would give to a human, right, are not what is actually necessary for the navigation of the robot. You don't really tell me to go forward by 1 meter, then turn right 45 degrees, something like that, right? It's clear that that wouldn't be a very, even if you think about it, that wouldn't make a lot of sense, right? You wouldn't tell, that wouldn't be very useful for a human, because if if I blindfold, okay, we can try that. So the 3 of you come up here, the 4 of us. Come. I just want to test a couple of experiments. You go there, and stay exactly on this point here, behind the line. Right? Okay. And you come here and stay back to that. Stay this way, but not touching. Okay. And we have a newcomer. Oh, he just left. Okay, then it's just you and me. Okay, stand behind the line, facing this way. And behind the line.
Behind the line. Which
Yeah.
line?
This line there. Yeah.
Yeah.
Yeah. Now close your eyes. Okay. And go forward by exactly 1 meter. Okay. And when you're done, then just stop. Okay. So now you can open your eyes. So the two of you actually started here, right? So your meter, you think this is about this far, right? You think your meter is over there. So I would guess you're totally off. Like I know my usual set length is about 1 meter. So without measuring, and you, how far did you go? You were behind the line. You were behind this line. So you walked about 60 centimeters. So telling somebody to walk forward by 1 meter doesn't really help much because no human is very good at walking forward by 1 meter. It's actually really difficult if you ask a couple of people how far they think 1 meter is in walking. And if I say now 10 meters, then it'd be even worse. So that's why when humans navigate, we don't, you can sit down, thank you for the nice experiment. When humans navigate, we don't actually use sort of Cartesian coordinates. Right? Instead, we use what's called a topological map, which is things like go to the stairs, and you understand that other people are going to figure out what stairs look like. We know what stairs are, right? We can find those, and then we can go down to the first floor or the second floor or something like that, right? And then you can go to the entrance of a building if you know which building you're talking about, right? You can get there. So that kind of mapping is the kind of mapping that humans sort of expect. Not always though. I mean, before Google Maps, people actually printed out city maps and things like that. That's if you needed to find sort of shortest routes to unknown destinations. But nobody would tell you, if I ask you how to drive to your house, nobody would tell you, go forward 250 meters and turn left, right? It's like, oh, in the US, it would work. You could say, oh, turn right at the 7-Eleven. In Taiwan, that would be a horrible direction because there's a 7-Eleven every block. So you can pretty much turn right anywhere you want and you'd still hit the 7-Eleven. So this kind of mapping that we want to do, the problem of taking a local snapshot of the environment, moving a little bit, localizing yourself within that snapshot that you just took, and now you can see a little bit more. That's called simultaneous localization and mapping. Localization is finding your position in a map. Mapping is building the map of your environment, the global map. Simultaneous means that we're doing both at the same time. Right? Localization, then mapping, localization, then mapping. what we're talking about today is visual SLAM, visual simultaneous localization and mapping. We want to be able to do that with a camera. And lots of research has been going on in this area for at least 30 years now. And one of the crucial components is really to measure, to be able to localize yourself, right? One of the cornerstones is to be able to localize yourself, which means you need to work out how the images changed while you were moving through the environment in order to be able to figure out what your position is. Now, technically speaking, this is really ego motion estimation. You're trying to figure out how you move with the images that you receive. It's sort of very technically speaking, I guess. You don't really need to localize yourself in a map. It would be sufficient to say that you drove forward by 50 centimeters and you turn 12 degrees to the left. But if you have that information, then it's also easy to just plot your point and now you're localized. But technically speaking, you don't really need the map at this point. And there's some applications that that are like that. So for example, with the scooter project that we have for our humanoid robot drives the scooter, one of the crucial problems was the fact that we needed the control very much depends on the angle of attack of the lean angle of your scooter, of course, right? But that one we can measure quite easily, but it also depends very much on the current velocity that you're driving at. And you probably realize that from bicycles. If you ride the bicycle, the faster you go, the less steering control you want to do. The slower you go, the bigger your steering changes are usually. And that means we need to know the exact velocity of the scooter if we want to balance it. And the problem there is that GPS is too coarse and doesn't work here in the urban sort of canyons at NTNU. There's quite a few spots where we have poor GPS reception. So GPS didn't work, and then how else do we get the velocity of the scooter that we're currently driving? Then one idea that we had was to have a camera, mobile phone, and point it at the speedometer and then just read off what the speedometer reads on the scooter, because the scooter has a display, right? It shows you like 15, 12 kilometers per hour. That one is quite, for our purposes, it would be accurate enough. It's connected to a wheel that turns as the wheel turns. But as long as it's not too slippery, that if you're driving on ice in Canada, that would be a different story. But here, we don't have snowstorms in Taipei, so that wouldn't be a problem. But that didn't work because we have too much sunshine. So once the sun shows onto the display, you cannot really read the display anymore. It's just like pure white. We also have a IMU in the robot, which is inertial measurement unit, which allows us to measure the angle. That's what we use in order to measure the current lean angle of the robot. It has a 3-axis gyroscope built in, so we can measure the angular rotational velocity, and it has an accelerometer built in. And with that accelerometers, the trick is that we don't really use it that much for um, measuring the linear velocity, how fast we're going, because in order to get the angular, to get the velocity, you would have to um, uh, calculate the derivative of your acceleration. So then you're looking at the differences of the acceleration, and that turns out to be very noisy. Any kind of measurement like that to get the velocity is going to be not very useful, especially then also if you have bumps in the road, which will also introduce additional acceleration in X, Y, and Z. What we use the accelerometer, it's very useful because the gyroscopes, they can only record angular velocity. So they don't actually give you 5 degrees, but they're just telling you how far you rotated. So we have at what, how many degrees per second you rotated. So we are kind of have the same problem. And then if you do that, it works really well at the beginning, but over time, there's little errors in your angular velocity estimate in your gyroscope, in your sensor, as well as in the timing when you calculate the actual lean angle. So that introduces drift error. So what happens is if you have the robot and you lean it to 10 degrees and then you pull it to 0 degrees, 10 degrees, 0 degrees, so the robot just does this. Then after you do this 20 times, the robot would be at 0 degrees looking straight up. But in fact, your not your sensor, but your program, your algorithm, the noise will have added up. So you'll be saying that you lean 5 degrees to the left or 5 degrees to the right or something like that. So that's a huge problem, this drift error in gyroscopes. There, the accelerometer can help us because we actually measure gravity and the acceleration due to gravity. And then it becomes, there's different ways to implement it, either using Kalman filters or complementary filters. Complementary filters are probably easiest to understand, but the idea is that when the robot rotates quickly, then the angular velocity is very accurate, right? Because there's a nice value that it can measure. But if the robot is sort of not rotating much, balanced, then there's not much angular velocity, so then the errors kind of drift in. But if the robot doesn't rotate very much, right? If it's at a stable angle, that means that the accelerometers are actually very nice and accurate. So as the robot is rotating quickly, your accelerometer data is not very useful. But if the robot is at a static, stable angle, then your accelerometer data is very useful and very accurate, and you can reset your gyroscope angle. So then you need to fuse those two readings. So that's a possibility. And what we really do is we're implementing Visual SLAM in order to get the velocity of the scooter. We actually run a full SLAM system on the robot. So we do the map and everything, but actually the main reason we just want the velocity. But with that, in the future, maybe we want to build up a map of the campus and things like that. So that's the idea. So first of all, before you can do that, we need to figure out how the images actually changed. Right? Because clearly, if I'm looking at the green wall here, and this is all I see, and then I can drive all I want calculations. If everything is a green wall, then there's nothing I can do in order to estimate my position. So I need to have some feature points, like we discussed in the last class, points that are either local, hopefully globally unique, but usually we don't get those, but at least locally unique, and you can exactly pinpoint their position, and yeah, they are invariant to changes in lighting, changes in scale, changes in rotation, and changes in translation. So those are quite complex feature points, but often we just refer to them as corners, even though they're not really corners of objects or anything like that. They're really specific points in the image that, but they have to be sort of like a corner in the sense that if they move, we can track where they move to. If we have an edge, like that edge of the column, then that doesn't really work, right? Because I won't be able to track a point. I can only track the point where if it moves, or the edge if it moves right or left, but I won't be able to track if it's moving up or down. That's called the aperture problem in optical flow then. So we need to have these points. Now, last time we talked about a corner detector, and you can really use any kind of feature detector that you want, any kind of corner detector that you want in order to start your Lucas-Canade optical flow algorithm. And then the idea is actually quite straightforward in the sense that you just need to keep track of the motion of these points. And then based on that motion, you're trying to map points to 3D coordinates. Once you have the 3D coordinates, then you can track the position of your robot. And a lot of that research is very closely related to stereo vision, because in stereo vision we take one picture at time t with two cameras, right? A right eye and a left eye camera. In optical flow, we take a picture at time t and we take a picture at t+1 with the same camera, but in a different position. And this one, actually, technically, this would be monocular, a single camera visual SLAM. There's also stereo vision visual SLAM algorithms which perform better in the sense because they can get the depth information easier or more robustly. So as I'm moving forward, then you can see in the video the points move towards the edge of the image. As I move backwards, the points move towards the center of the image. If you look at the trajectory, when I rotate left, then all the points move to the right. When I rotate right, then all the points move to the left. So most of the points are going to move, but not all the points will I be able to track. So in this particular video here, this pixel here, right? If I track that, I'm not going to be able to detect where that moved to because it doesn't really have locally any unique features that I could use. If I want to track something, then this point here would be a much better candidate. The bottom of the column there, the bottom of this board, and the end against that column, and you can see This here would be a globally unique feature point. Here I have a couple of feature points that all look similar. So I have to make sure that I don't mix those up. So these points, these trackable points have to be static. They cannot be moving themselves. So if your feature point is on a dog that runs through the image, then that would not be very useful. So they have to be static, they have to be in the scene, remain in the scene until the next frame at least, so we can track them. Have to be unique in the global image or at least the local neighborhood. Robust to changes in the viewing angle, illumination, brightness, rotation, and scale. To determine the distance to points, um, with a single image, we can provide information about the vector from the camera to that particular point. So that gives us a line, but we don't have any distance information. And then various solutions, either stereo vision, which means that we use two cameras. Now, people initially thought that stereo vision would solve all the problems for computer vision in robotics, because people have two eyes, so obviously our robots need to have two eyes. Turns out that human stereo vision is actually rather short range to what you expect. So anything that's like the distance of the door there, the parallax shift between the right and the left eye is very small. So your brain cannot really use that in order to accurately determine the distance to objects. Not with the kind of accuracy that we would need in order to be able to build a map, for example. But we use it for doing things like threading a needle, like something with your hands, where you need to be very precise in the 3D orientation. Then the stereo vision is important. Rangefinders, so those are different methods for getting 2 points, but actually vastly expanded parallax. So so you use mirrors, and they were used a lot still during World War II. Not World Wide Web. Yeah, so they kind of look like this. So you have two mirrors on the side, then you can shoot out the thing, then you can get. Then it's like having eyes, but your head is like this big, right? So with that, you can then triangulate the position of the point, and it's much more accurate. And they used it on ships too.
What exactly is parallax?
Parallax is the shift from a particular point, like your finger, the top of your finger. If you use right eye, left eye, then that finger jumps. That shift is the parallax. And for humans, if we do this kind of estimating distances to objects, we don't actually, for objects that are far away, like the door, we cannot actually use the stereo vision effect. It's actually the size of the objects that we use more often. And there may be, we can also use additional knowledge about the objects in order to position them, in order to get the distance. So for example, if I know that something is on the ground, then I can better estimate the distance. I can actually calculate it with the camera if I know the position of the camera. Let me see if I have, there's a very good magic trick. There's a couple of magic tricks that use different sized cards in order to make it look like you're doing the impossible. I cannot find the one that I wanted to show. So clearly points in a uniform region are bad because they give us no information. Like the white of the table, points, pixels in here are not going to be very useful. Edges are better, but they only allow us tracking in one direction, not in two directions. So corner points are much better because they allow us to recognize movement in two directions. So optical flow is an interesting algorithm because in most of computer science and robotics, the algorithms that we discuss, they have this tendency to become more and more complex. Right? So, for example, we started with simply looking at the differences between pixels, right? Then at the Kirsch mask and the Sobel edge detectors and convolution masks, and then the latest algorithms for edge detection, which is a very simple problem, you would think, are the Canny edge detector, for example. Now, the Canny edge detector is sort of building on top of Sobel and then has more complex processing in order to detect edges more accurately. Non-optimal non-local maximum suppression, so that you only get one edge pixel along an edge and things like that. So there's a tendency to make the algorithms more and more complex once we understand the simpler algorithms. Right? And to deal with more of the edge cases, in a sense. Optical flow, I kind of like it as a problem because what's interesting is that as your algorithm becomes more complex, it also usually slows down, right? The processing speed will be slower. Now in edge detection, that doesn't really matter because if you're reading, nowadays you can run image edge detection at thousands of frames per second if you wanted to. Wouldn't make much sense if your camera is only delivering 30 or 60 frames per second. So that extra computational effort is not making much of a difference in edge detection on static images, for example. Trying to do this in Photoshop. Should have used that example. If you do that edge detection in Photoshop, if it runs in 1.2 milliseconds as opposed to 1 millisecond, then that's not a huge problem for the user. Right? I don't think any application will be negatively affected by it. Optical flow is interesting because if you think about it, what we're trying to do is track the movement of the pixels, right? And if you could actually read your camera image, right? If you can actually read that at 1,000 frames per second, then optical flow would be trivial, because for every pixel you just need to look at one of 9 neighbors. And if your frame rate is high enough, that pixel cannot possibly have moved any further than 1 pixel. Right? So you're looking at a very small neighborhood only that you need to process in order to find where that pixel has moved to, basically. But if you now have a more complex algorithm and it takes you twice as long, now all of a sudden you need to look at the 4x4 neighborhood. So you need to look at 16 pixels all of a sudden. Right? So the more complex your algorithm is, the more clever it has to be, which means usually it will run even slower. Whereas a simple algorithm may perform just perfectly fine without any complex additions to it. So in this case, it's one example where the extra computational cost, because the size where the pixel, the area that the pixel has moved to, grows with the square of sort of the maximum speed that your pixel moves, right? If it can move by a maximum of 1, you just need to look at a 3x3 neighborhood. If it can move with a maximum speed, which is 9, right? If it moves by maximum speed of 2, because your algorithm is more complex, now you have to look at a 25 pixels neighborhood, which is more than twice as big as what you had before. So this is a kind of interesting feature of the optical flow problem, that many other problems in computer science usually don't have this kind of trade-off that you need to be aware of. So the Lucas-Canade algorithm for optical flow is one of the first optical flow algorithms, and it uses the Shi-Tomasi feature points, which are available in OpenCV as good features to track. They're very similar to the Harris corner detector that we implemented last class. They calculate the same matrix, but they use slightly different feature descriptor. So we calculate the least squared error for a position of a point in the new frame, and we're trying to minimize the squared difference between the neighborhood of pixels in the previous frame and the new frame. And the xy that offsets, that minimize that difference, that's the estimate of the optical flow. And then there's an extension, like there always is with the algorithm. So this is the standard Lucas-Canade algorithm. Then there's a weighted Lucas-Canade algorithm, which, when it calculates the least squared error about the old position and the new position of the pixel, it weighs the pixels that are in the center more heavily than the ones that are on the outline. And the reason for that is because any ideas why we would like to prefer pixels that are in the center of the image rather than on the edges?
Some people will tell you shit.
The center will tell me what?
Some people will tell you how you shit.
The edge would do that too, no? Like if I just go like this, one step, then all the pixels should shift. All the pixels at the same distance are going to shift by exactly the same amount.
You use the center as the reference.
No, not necessarily. I mean, it doesn't have to be the center of my world coordinate system or anything like that. The first reason is, let's say, if I take this point here, right, this pixel there, then if we run the video, okay, then what happened? It leaves the frame, right? So that's where we end up with lots of noise in the image, because now um, it's like the way that we build algorithms, right? We're trying to track pixels. So we're trying very hard to find the new position of the pixel. But if that pixel disappears, then I'm trying very hard to find some other location that is still reasonable, which will then be completely wrong, which usually ends in catastrophic failures for a robot, because the robot thinks that there's now obstacles everywhere. He's refusing to move anywhere. So the first reason is that pixels in the center of the camera are more likely to remain within the frame. And depending on, there's also if it's a wide angle lens. Right? The second reason is the more wide angle your lens is, the more distortions you have at the edges of the pixel. So even if you can track the pixel, the movement wouldn't be exactly linear. It may look up like a curve or something like that. The center is usually more more aligned with what you would expect. So here's an implementation of the Lucas-Canada algorithm. What did I call that video? So this is our test video, and then we need to run two algorithms. One is the actual feature detection, the corner detector, Shu-Tomasi, which has a number of parameters. In particular, the maximum number of corners that we want to track, the quality level of it, and the minimum distance between between different feature points. We don't want them to be too close together. And then the size of that matrix that we actually use, the size of the environment that we use in order to check for any movement of the pixel that we get a strong response. And then the Lucas-Canade algorithm, which has a couple of parameters, in particular the size of the window that we're checking. We're tracking the pixels. And the max level is if we move very quickly, then the scale invariance becomes a problem. Because basically we're not tracking one pixel anymore, because if I go in now, it would be 4 pixels all of a sudden, right? So in order to get scale invariance in our computer vision algorithms, we either blur the image repeatedly, iteratively, in order to get rid of lower features or like local features, right? They will be averaged out then. Or we actually zoom the image. So SIF does the blurring and SURF does the zooming, basically. But they are both they're both trying to do the same thing. They're trying to remove the local features and build them up into larger ones that are then at the same scale level as the original feature. Now, if your objects, if the points that you track, if they don't change that much in size, then you can speed up the algorithm by just doing one level of this scaling. So in that case, now if we move very fast and points are like 10 meters away, now they're 10 centimeters in front of me, the scale would definitely change. Those are always very hard to track anyway. So in this case, to make it run a little bit faster, I just set the maximum level to 1, which means we only run it in one level. We're not really invariant to scale at that point. And then I just create some random colors and take a frame, calculate the features as my initial point. And then here is the neighborhood of the point. 10 by 10 region around that point, and where we found the old frame and the new frame. And here we're just showing it, and they move from 414257 to 407252. So the region, the left one is the first image. It was 404, 425, 404. From y coordinate 404, 424, and x coordinate 247 to 267, and then 397, 417. Then we can run the Lucas-Canade algorithm. Okay, and as you can see, I actually didn't swap the color channels correctly. That's why the wall now is blue all of a sudden instead of orange. So actually, let me try and run this a little bit. I just want to make that a little bit smaller and then fix the colors. Okay. Okay, then I just want to change the size. See if I copy it, then so now our colors are correct, and here are the points that it found that it's trying to track. So here we can look at the motion of the points. And that's kind of cool. Doesn't seem to have made any large errors. If you look at the code, that's the standard outline for the Lucas and Canale optical flow algorithm. The set of points that we're dealing with is P0 here, and then we can extract the points with different features, so the status has to be 1 saying that it's found. If we cannot find a point anymore, then we'll set the status to 0. So here it feeds in the first set of points that it's trying to track, and then this will be P1 as the output. And then we have the good new and the good old points, and then we can draw the lines between them. And then the new points become the input for the next iteration of our Lucas you can see so here, for example, this point was lost, so then it disappears. We didn't track it anymore. You can also see how light can cause a problem for these kind of tracking algorithms, because one of the it didn't do in this particular scenario, but these highlights here, these reflections of the light on the ground, in one frame they would look like really good points to try and track, because they're very clear corners, very easy features that we could track in the image. But unfortunately, they're not static, because they change as you move. The reflection of the light is going to change as well. So luckily, our algorithm didn't pick up on those. Another problem for this kind of visual SLAM, if we look at the pictures, I don't know why my mouse has to be off this. You can see we have quite a few points here on this cluster, here, here, here. So there's really only 5 locations in the image where we can track points. That's not ideal. Ideally, you would like to have the points all evenly distributed across the image. That's usually not possible, but at least that's the goal. So that you get 3D information about the whole environment. Like, the problem with having no pixels here is not that we will lose track of where we move, but if there's a flower pot in the image or an obstacle, we wouldn't be able to recognize it, right? So in a sense, this area here, right in front of the robot, would be a lot more important, right? Because if it tracks objects, like these pixels here, these points here, are what? 10 meters away from the robot. By the time the robot goes there, something may have already changed. So even if there is an obstacle in the way there, it's not an immediate concern. Here, this is where you would bump into people or obstacles or run over a little kid or something like that. So we have 2 views of time. Basically, one is moving in the forward direction. So we stop tracking points that moved out of the frame. For more robust implementation, we can also see if we can track points backwards, so that there are points that were also in the previous frame already. So we can track points through time from the start towards the end. We also want to be able to track points backwards from the end towards the start. Those will be the most useful points. Distribution is non-uniform, so we can fix that by taking the best features in different parts of the image and use those as as the pixels that we're trying to track. Now, also, if you look at the algorithm here, the biggest problem is that we track points. If they're in the old frame and they're in the new frame, then we keep them, right? If they're in the old frame but not in the new frame, then we drop them. So for example here, uh, you watch this pixel here. This pixel here that we switch to, right? That moves out of the frame now. So now it's gone. So before I have 10 pixels that I'm tracking, now I have 9 left. The problem is we drop pixels, but we never actually add new pixels to the frame. So that obviously would result in our algorithm eventually dropping all the pixels once they all move out of the view, and then we are kind of stuck. So for a more robust implementation, what you want to do usually is to keep, let's say, 75% of the points that you have and add a new 25% of the points. So run your your corner detector every frame, and then add the top 25% of the points that are not that you're not tracking already, so that you always have points to track in your. So um, so here, for example, I split it up into the top and bottom frame for at 320. Left and right, not top to bottom. No, no, no. Top to bottom. From 0 to row 320 and from 320 to the end of the picture. yeah, just didn't correct for the colors yet. We have some more pixels then. So I can also use um, different parameter settings in order to find different parts of the image, which is what's usually necessary. Like, so then now we also have some pixels here towards the bottom of the image. And then we can do some experiments. So for example, here, uh, I can skip 10 frames, which now is the same thing as having a much lower frame rate. Right? So I only read one frame and then I skip 10 of them. So that would be either your frame rate is much lower or the points move a lot faster. Now full frame rate. forgot to cast it to integers there, which seems to have been something that was allowed before. Get rid of the print here. Yeah, now we have a much shorter video because it's only 2 frames. And now it's also a lot wilder. Like there's more chance of it missing some pixels and misjudging the movement. So there we can have a mess. Okay, good. So this is the Lucas-Canade optical flow algorithm. Quite useful in lots of applications. Many computer vision algorithms are required, or that kind of processing, tracking object through time is basically what we're doing. One of the biggest applications is Visual SLAM, monocular Visual SLAM in particular. The other one would be structure from motion. Right? It's also the cornerstone for structure from motion, where I want to get a 3D Blender image of a particular object. Right? One way I can do that is move around the object and then see how the points change as I track other points in the environment in order to figure out what my new camera position is. Right? So doing that, I can then get a 3D model of the object that's in front of me. Both of those are based on the same kind of idea, tracking points through time using a monocular camera, like a monocular vision system, just a single camera. And that's possible, and the algorithms have grown quite sophisticated and powerful. There's also recent work on supporting the algorithm using deep learning, and that's kind of interesting. There's been some early work by Dieter Fox where they actually ran the optical flow algorithm in order to generate some training data, and then they trained the neural network to basically reproduce that. And then the cool thing is that basically the robot can drive through the environment, but instead of tracking Shu Tomasi features, it would basically learn itself what features are useful to track or not. So for example, if there's a lot of points, it would consistently mislabel. For example, here on this particular floor, the crosses may look like perfect features to track, right? Because they are very unique. You can rotate, translate them, you can track their orientation and position very easily. But the big problem is that if I move this far, now I'm looking at this corner, right? Then I can very easily detect my movement. But if I now go this way, and now I think I'm still back there, the two crosses on the floor look the same. So there's no way to distinguish those two. So then the algorithm will be able to overcome that by then saying, okay, I know these are really good corners, but don't track them because over the entire run of the through the environment, we would end up with false positives. Or false matches, not false positives, false matches. Because you wouldn't be able to say if you moved 1 centimeter or 1 whole square or 2 squares or 3 squares. So then that makes it difficult to build them up. Now, the early algorithms, there's another one, Horn-Schunck. Works similarly. What we have so far is what's called a sparse optical flow. So I don't really know how all the pixels in the image move. The only thing I know is how certain feature points that I can track, how they move. Now, for some applications, that's sufficient. Very popular for Visual SLAM. That's all we really need for that. But in other applications, we want to have not just the feature points and track those, but also the surrounding pixels. Now, how can we do that? It's kind of like a dispersion algorithm or a relaxation algorithm that you apply. For example, if I'm here and I track, I'm trying to do my optical flow, then I can not really detect any of the features in the white tiles here, right? They're all just white pixels with some texture to it, but let's say we cannot recognize it. I am able to track the position of the two, let's say the two crosses there on the ground. Now if I move a little bit, then I know this and rotate, then this pixel will have moved down and this feature will have moved up in my image and the whole thing was shifted down because I also moved forward. So now I can kind of interpolate, right? I can figure out what the motion was. This one moved by this much, this one moved by that much. So I can sort of guess what the pixels in between were doing. If I have that for enough pixels, then I can calculate what's called the dense optical flow. Now, there's additional information there that we need to concern ourselves with. If I do see that edge, for example, then that kind of limits the way that the movement can occur. So the gradient of the pixel means that if that pixel would have moved backwards and forwards, then I would have recognized that. So if it didn't, if it's in the same position, that means it can only have moved this way. So that means even though we have a uniform colored region, I can still calculate what the movement of the pixels in between these feature points were. If I don't have any feature points, there's no way that this will work. But if I have some kind of contour that I'm tracking, then I can also figure out what the pixels near that contour line would have been, even if they itself would have not been selected as feature points to track. And the Farnaback algorithm is the most popular algorithm right now for dense optical flow. but it's basically working in the same way. It just has this additional step of interpolating the pixel areas around. Okay, then that's a new one now. And so here's our test video. So now we use the Cog optical flow Farnebeck algorithm that takes the previous frame and the next frame and then calculates for all the pixels the the direction, the angle of movement, and the magnitude of the movement. So here you can see the optical flow now densely populated for all the pixels that are sort of in the region. You can see there, here we're now tracking the light, but that is not actually such a good choice. The floor kind of move at different speeds. These shift as well. Right? They should be all the same because the entire floor is moving at the same velocity towards us, approximately. Here in the back it works well. Okay, let's put it there. And then let's have a look at this environment here. So here one time when I used the Farnaback algorithm was we were in Kaohsiung and we were supposed to take part in a computer vision competition that was organized by NCKU, I believe, and didn't really have much time to prepare. So then the afternoon, students hadn't really made much progress, and the problem that they had was um, counting the number of pedestrians that walked into the flower expo. I think that was one of them. So because they need to have they could have a maximum of 5,000 people, so they put cameras, um, and then they would track how many people walk in and how many people walk out. And that was the actual challenge for the competition. Then you had to implement an algorithm that will count the number of people. Now, I didn't spend that much time on it because I'm more interested in robots and computer vision and counting. But anyway, we thought we should take part in it because a good friend of mine organized it. And it's a non-trivial problem. Let me just try and find the. So was this conference 2014? Oh, it's been a while. Let's see where the. So this is the videos that. Yeah, I remember that it had something to do with flora. So here you can see this is the simple version of the problem, but you can see it's non-trivial, right? Like here, okay, you may think, okay, the camera is looking down, I just need to count how many pixels are moving across there, right? How often that happens. But turns out that that wouldn't work here, right? Because now 3 people move through at the same time. So if you just have kind of like a light gate and you implement that at vision and you check how often that's broken, then that's just going to trigger once in this case, but 3 people just left. They're also not moving exactly through there. You have children. Pick one from the Flora exhibition. So there, counting the number of people is even harder, right? There's no red gate. There's one point, somebody's pushing a stroller through the picture, and then it's not even clear to me because you can only see the stroller, but you cannot really see the baby. So is this like a person or a half a person, or what should be the correct output there? That was certainly then people are rushing through, going the other direction. And
umbrella there falls an empty
oh,
wheelchair.
yeah, empty wheelchair on the umbrella. So not easy, right? You would have to hire a person if you wanted to do this very accurately. So that's what we were trying to do. And so I reconstructed this scenario here in class. We can do it again, but I think the video will look pretty much the same. So now I need to download this. And, oh, pedestrian one. E4. Pedestrians one. So just for fun, we recreated that here in the lab. And you can see people walk through. Now they're trying to run, or I make them run. Some people bunch together. So in order to calculate the optical flow, one simple idea is clearly that we're looking for the differences in images. So one of the ideas is to just calculate that, right? Like actually calculate, subtract new picture from old picture to look at what the differences are. And then the things that changed is part where there is motion, and the things that didn't change, there was no motion. That would be sort of the basic idea. And that, of course, after COVID, everybody's familiar with that kind of algorithm because people like to blur the background in their Zoom calls, right? Or replace it with the beach so it looks like you're sitting on the beach. Or you, even worse, you're a grad student, you are at the beach and your professor calls you, you want to make it look like you sit in the office, right? In the lab. Different applications for that. So in this case, we can try and see how that works. I can just take the absolute difference between the two frames and then show it. So this would be the frame. This is the difference to the previous frame. You can see how things change. Actually, not that easy. Because, for example, the shadow will also change things. So there will be some difference for the shadow. Even here, the keyboard, which didn't move at all, it still shows up as different because just of the fact that it's occluded. This one in the front here would be the shadow. So we need to be a little bit smarter when we do a background subtraction because just taking the frame by frame difference is very noisy, pixel by pixel. Shadows change the value of those pixels. So what is usually implemented is that we measure both the average brightness of a pixel as well as the standard deviation of every pixel in the image separately, and then label only pixels that are more than n standard deviations away from the average as foreground pixels. That is also important for things like the fluorescent lighting that you have, which flickers at 60 Hertz. So the brightness actually changes, but it's too fast for your eyes to actually recognize it. But the camera will actually recognize it. That's why if you take pictures of the old TV screens, you can see the flicker as well. And I actually read somewhere in a case uh, in the UK, this particular flicker, the lighting also changes based on the power that you get from the power station. And this was actually used in a murder trial where they were trying to prove that that person was in that particular scene at a particular time in a particular location. And so they had the time of the video, but they didn't have the location. And he said that video was taken in Cambridge. But actually, the murder was committed in Oxford, something like that. They actually proved that that particular video was taken in Oxford by contacting the power company, and they actually have, they record this anyway, and they know exactly what the power fluctuations are. Then they match the lighting changes in the video from the indoor scene to the power fluctuations from the power station in Oxford. So they could prove that the person was not, it was kind of like an Agatha Christie, Sherlock Holmes kind of thing that they did. But that seems to be something that they do routinely in the police investigations. I just never heard of it before, but thought it was pretty cool. So then they would do the same thing. So we estimate the average and the standard deviations of the pixel. We use that with our soccer playing robots as well. We subtracted the playing field out of the image, and we basically implemented exactly that algorithm. Now, you can implement this by hand, but there's also OpenCV function, background subtractor, mixture of Gaussians too, which takes a look at the 100 last frames in order to estimate standard deviation means of the pixels. And it can also use a method to detect shadows, which will be a universal drop in brightness and variance for a region. Then here's the output of the mixture of Gaussian. You can see that's a lot less noisy. Right? We do have some problems with the pixels on the edges here. They vary. But other than that, it's pretty solid. So then here we can they really must have on that. So this is the Lucas and Canade optical flow algorithm on that input data. So we can track those from the previous frame to the next. And then we can also run the Farnebeck algorithm. Here we just show this one more time. So here we can now track the different shapes. This, and this is what we implemented for our pedestrian detection algorithm. Um, and here's the GitHub repo that you can have a look at. I should upload the algorithm. Basically, I put the optical flow into different buckets for different directions of movement. I was only interested in the one that was going through the gate, through the door, and then just kept adding on bolts. So it's kind of a little bit inspired by the Hub transform, and then we can draw the forms that we get. Something will change. And what does we do an animation? No, we just get the frame version, and let's fix. Must be an integer types. Okay. Let's see what that actually is.
is it not happening on this?
Okay, I think that's it. Now you can see how the person entering, we basically put in all these buckets in the direction of the movement. So here we have our beginning and the different frame sets. So the buckets simply keep track of which direction the movement was, if they're entering or going backwards. And that was actually quite successful. We won second place in the competition. The only thing we had to do is, at the beginning they showed us was kind of sample videos that they had, and then I just calculated the total sum of all the movements in a particular direction, divided by the number of people that we counted in the training video. So we only have to watch the training video for a couple of seconds if there's 10 people walking through. Because I didn't know how much change there would be for a person walking through. But if I count 10 of them, then I can sum it all up, divided by 10. That gives me actually a pretty good, pretty accurate estimate. So that worked really well. Now, let me just fix this here. I don't want to do that. I want to. Here's our figure. We show the image. So let's skip the first 5 frames because there's nothing in the video at that point. Um, this goes. I have a meeting starting at 12, so I think you will have to watch that video on your own. I'll have to leave in a second. But that's it as far as optical flow is concerned. A very useful technique in several applications for computer vision, especially if you need to track amorphous things or count them, then that worked quite well. Okay, then I'll see you next week. And I need to stop.